Hello, my name is Christopher Fabian. My student number ID is 21055531079, and my lecturer is Prof. Dr. Tjokorda Tirta Nindhia STMT. And we're gonna talk about now is about metal forming processes, chapter 2G until 2L. Okay, let's continue. What is the content of this presentation? So today, or right now, we're gonna talk about HERF, or we as known high energy rate forming methods, and then we're gonna talk about strengthening and other forming processes. High energy rate forming methods, or HERF methods. The principle of HERF is the energy of deformation is delivered at much higher rate than in conventional practice, and then larger energy is applied for a very short interval of time. High particle velocities are produced in contrast with conventional forming process. The velocity of deformation is also very large, and hence these are also called high velocity forming, or HVF processes. Many metals tend to deform more readily under extra fast application of force. Large parts can be easily formed by this technique. For many materials, the elongation to fracture increases with strain rate beyond the usual metal working range until a critical strain rate is achieved, where the ductility drops sharply. For sure, the strain rate depends on the strength of the strain rate depends of strength increase with increasing temperature. The yield stress and flow stress at lower plastic strains are more dependent on the strain rate than the tensile strength. High grade of strain cause the yield point to appear in tests on low carbon steel that do not show a yield point under ordinary rates of strain. So that's all the principle of HERF. Advantage of HERF methods. The first one is the production rates are higher as parts are made at a rapid rate. And the second one is the costs are relatively lower, and then tolerance can be easily maintained. And versatility of the process, it is possible to form most metals, including difficult to form metals. No or minimum spring back effect of the material after the process. So when you processing, because of the heat, it's gonna to make it stay at the form, the after form, look like when you do in the cold working. So in the cold working, you need to extra force. Production cost is low as power hammer or press is eliminated in the process, hence it is economically justifiable. Complex shape profiles can be made much easily as compared to conventional forming. The required final shape or dimensions are obtained in one stroke or one step, thus eliminating intermediate forming steps and pre-forming dies. And then the last one is suitable for range of production volume such as small numbers, batches, or mass production. Now we're gonna talk about explosive forming. So in explosive forming, a punch is conventional forming is replaced by an explosive charge. So when we talk about forming, it's gonna be a die, and then there is a press, like this is the die and this is the press, it's gonna be like this. But the difference between explosive and conventional forming, in explosive, the punch is changed by the wave of explosion. So normally the explosion takes place in water, and the water pressure, because of the explosive, reinforces the work metal against the die walls. But rubber, sand, glass, oil, molten salts, and air also can be used in process transfer medium. So the water after the explosion causing the waves is gonna be push the metal part into the die, so it's gonna be like this, as you can see here. So this is the explosion. The explosion caused the wave, so like this caused the wave, so it's gonna be filled on this part. This part gonna be filled like that. So that is the unconfined type explosive forming. The different just the unconfined means it has no confine, and this has confine or cartridge. So that's all. The explosive can be TNT, RDX, dynamite, propellants, and gaseous mixtures. So here is the video.
Explosive forming is a metalworking process that uses energy from an explosive to form a metal into the shape of a mold. The sheet is placed on top of the mold and the air beneath the sheet is evacuated. This is done to prevent the air from stopping the metal sheet from being pressed into the mold once the explosive is triggered. Next, the tank is filled with water to maximize the effect of the shock and pressure wave. Finally, an explosive is placed above the metal. When the explosive is triggered, it creates a shock and pressure wave.
As you can see, this is the explosion causing the waves to push the metal part
When
into
the
the
pressure
mold.
wave hits the metal sheet, it then forces it into the shape of the mold.
So that's all.
Explosive forms.
So now combustible gas forming. Combustible means explosion as well, but it's slowly. With this half process, hydrogen, methane, or natural gas mixed with air, oxygen, or ozone, when ignited provide the pressure wave that forms the sheet metal workpiece. The pressure wave occurs in the ignited gas rather than in water or some other medium. The process is more suited for in-plant operation and for larger production quantities than high explosive forming. More complex shapes can be produced as well. So the difference between the previous one, it used the electrical connection, the oxygen and combustible gas wouldn't, and it's gonna be like, if you know, like when in motorcycle we have like something to start a fire, so I need the electrical connection to start fire, because the mixture between oxygen and combustible gas inlet is gonna be fire by some small fire, so it's gonna be pushed because the small explosion here, and the workpiece gonna fill the die cavity. Electromagnetic forming or magnetic pulse forming. The electrical energy stored in capacitor bank is used to produce opposing magnetic fields around the tubular workpiece, surrounded by current-carrying coils. The coil is firmly held and hence the workpiece collapses into the die cavity due to magnetic repelling force, thus assuming die shape. There is no contact between the coil and the workpiece, and the magnetic energy will be passed through the non-conductive materials such as fiber, rubber, plastic, and other parts. So this is the workpiece, and you can see like this one, the gray one, and this is the capacitor bank, of course, and this is the coil. The coil and the tube here is covered, like this is the tube and some like non-conductive materials, and then the next one is like the coil. So after the coil being activated by the electrical things, it's gonna push the tube, so it's gonna be like this, from like this, from this, like this. I mean, this is the after, the before is like just straight, so this become like this, and it can be like using for mandrel, but the different one is it's gonna be put inside the tube, and then the electrical gonna push to the outside. Video of electromagnetic forming. So it happens inside the battery, inside like something like small cage. So this is the final part. Oh no. Yeah, this is the final part. It's for the coil inside the. Spark discharge forming or electrospark forming. Both this method and electrohydraulic forming described below use electrical energy stored in a bank of capacitor to create a shock wave, which is transferred through a liquid medium. In spark discharge forming, the energy release is in the form of spark, like the previous one, the explosive. Switching circuit instantaneously discharge that energy to the two electrodes. The intense energy emanating from the spark sends a shock wave that forces the workpiece material against the die walls. So, like if we remember the previous one on the explosive, this is like the explosive, but on this the spark discharge forming, it's gonna be changed into the electrodes and the cathodes. So the electrodes gonna be put here because of the electrodes and the spark. The spark pressure is gonna push the workpiece into the mold cavity. So that's all the difference between the spark discharge and explosive. A sudden electrical discharge is electrohydraulic forming. A sudden electrical discharge is in the form of spark is produced between electrodes, and this discharge is produced a shockwave in the water medium. The shockwave deforms the workplates and collapses it into the die. The characteristics of this process are similar to those of explosive forming. The major difference is that the chemical explosive is replaced by a capacitor bank, which stores the electrical energy. The capacitor is discharged through a charging circuit. When the switch is closed, a spark is produced between electrodes and the shockwave, or the pressure pulse is created. The energy release is so much lesser than that released in explosive forming because it's using the electrical somethings. Okay, this is the cathode, electrodes. Because of the connection between these two, it's gonna be caused like the pulse or a shock wave because of the electrical things. It's gonna be pushed the die cavity, the workpiece into the die cavity. The vacuum is used to make the cavity is empty with the air, so it's easier to push it. Pneumatic mechanical forming can be considered a variation of the primer forging, compressed gas stored in a pressure tank, or the energy released in the form of gas from combustion of a fuel oxidizer mixture is used to drive the press run to high velocity, 2 to 10 times that of conventional drop hammers. So this is the combustion. Combustion gonna be post here. This is the workpiece, and of course it has mold. Because the explosion is gonna push the hammer, because the force from the explosion gonna push to the bottom into, and this ram gonna be, or this hammer gonna punch in Indonesian accent, but in English in punch the workpiece, because the impact is gonna fill the mold cavity. Pin forming is a forming process that does not require any dyes and can be performed at room temperature. The sheet metal is impinged on one surface with a stream of metal shot, as illustrated below. The shot piece acts like a very small hammer stroke, compressing the surface vertically, not but elongating it horizontally. The shot is delivered by either nozzle or centrifugal wheels like the on 1H on the previous chapter. So it's gonna be throw or shot by the nozzle. Because of the shot, the form of fish gonna be like bended. Straightening. So now we get into the straightening. Straightening is required when the workpiece material is not the form required for subsequent operation, like coiled rather than straight, or has undergone some deformation from stresses induced by prior operation. Several methods are available. Straightening is to use external force or heating to extend the short fiber of the steel or shorten the longer fiber. Finally, the fiber length of each part tends to be the same, thereby eliminating the bending, twisting, uneven deformation of the steel or the workpiece. So this is the previous one. Because of the straightening, it's gonna be like the A picture. So it's compressed, and the last one is gonna be tend to tension, and it need to be like the same length. So we're gonna need the straightening. Manual straightening covers a variety of operations performed with surface plates, layers, pieces, anvils, hammer, twisting tools, groove blocks, and heating torches. Typically, the workpiece is clamped at one end or where there is no deformation, and the deformed part or the portion is moved in the opposite direction of distortion. The workpiece is overbent so that it springs back to straight orientation. Hammer blow or heat sometimes aid in the process. So we can see here it's gonna be like at this one is gonna it's gonna be beaten by the clamp, and the hammer gonna punch, and it's gonna be like pull while it's gonna be like keep hammering the thing. So it's gonna be like straightening. After the process, it's gonna be like this. From this, because of the straightening, it's gonna be like this. It's gonna be like this. Press straightening uses an arbor or hydraulic presses to make decorative bends. Typically, the deformed workpiece is placed on support blocks in the press bench so that the convex area is on the upward side. The ram descends and bends the workpiece in the opposite direction far enough so that the elastic limit of the material is exceeded. If done properly, the workpiece will spring back to a straight position. Local material can be processed with this less than 40 times 40 and times 40 hardness in Rockwell hardness. So this is the previous one, the blue one. After the press head, like many times, gonna punch the bended one. After the several times of punching, it's gonna be like straightened. So that's all. So here's the video. can see this is the bed. This is the bed. It's gonna be punched with a hammer, okay? Slow or velocity. So it's gonna be straight. Okay, that's all. Parallel roll straightening, illustrated in figure 2K3, is used on sheet, rod, or wire. A series of parallel rollers on opposite sides of the workpiece subjects the workpiece to progressively decreasing reverse bends as it passes through the rollers. As the metal is bent back and forth, it is stretched slightly beyond the yield point, exiting from the roller with a reasonably flat or straight sheet. The operation is rapid since it is continuous. So from the wrinkle one, like this, it put into parallel roll straightening because of the many. Of course, there is force here, force here, force here, force here, and from the each rolls, because of the force, it's gonna be straightened. So from here into like become like this, just straight, you know. So here I have the video of SPM plate straightening. So it has a lot of rollers. It has 9 straightening rolls, the 5 on the bottom and 4 on the top. Yes, this video is from Turkey because the product is from Turkey. So this is the previous part. It's gonna be rolled into the 9 total of straightening rolls. This is the final product, and it has strength. Look at this, so beautiful. That's all. Rotary straightening is a method of straightening round rods and bars. It uses 2 or more rollers with axes at an angle to each other and at an angle to the axis of the part. One of the rollers have concave shape as shown in figure 2K4. While the other is cylindrical, there are guides to position the direction of the rod to be straightened. Both rollers are driven by the workpiece and cause it move axially. As the workpiece moves, the curvature of the concave rollers puts the workpiece surface into the alternate stress of compression and tension. The angles of rollers and the pressure that they apply are both adjustable. So as you can see, the angle of between the this is the workpiece, this is the concave shaft. Because of the concave shaft, it's gonna be straightened because it has, of course, force as well, and it has the angle of axis and the part. So that's all how to make it straight. Like how do I do? Like this is the workpiece. Because of the wrinkle, like the bended one, because of the pressure, like here, and like here, it's gonna be put the workpiece into that side. It's gonna be like straight. If you can see, like this is from the front view. How do I do this one from the front view, and this part. So the workpiece is gonna be from here. It's gonna be straight. Now we're gonna talk about epicyclic straightening. Is a proprietary process for straightening axles, tubular drive shafts, and propeller shafts, L-beam, and other sections and symmetrical forgings. The workpiece is supported on its ends and is rotated. A powered arm attached to the center of the workpiece deflects the center of the workpiece so that it is stressed in all directions beyond the elastic limit. The powered arm reduces the magnitude of the deflection gradually so that the neutral axis of the part describes either a circular or elliptical spiral towards the center. As you can see here, the driver roll is gonna be like the bending roll. So this is the work part. It's like moving like otherwise. So it's gonna be like, to make it straighten, it's gonna be put like that. Straightening. I'm sorry for the typos. The workpiece is gripped mechanically and stretched in a straight line beyond the yield point. Twist deformation can also be corrected. When this is needed, the workpiece is reverse twisted when it is stretched. The process is normally limited to the workpiece of constant cross-section. It also results in material loss since the ends damaged by gripping must be removed. So it's gonna be like beaten by the gripping jaws because of maybe it's wrinkle one, because of the push and like this. It's gonna be like this, and after the stretch, it's gonna be pulled again, and it's gonna be a straight line of the workpiece. So this is the video. So that's it. Powder metallurgy processes. Metal powders mixed with certain solid lubricants are compacted under pressure to form the desired shape. Metal powders mixed with certain solid lubricants. Okay, this is the reason. The center part may be pressed a second time to improve dimensional accuracy and surface finish, and sometimes to modify the shape. Typical powder metal parts are rather small, about 3 square inches. and in cross-sectional area is a typically maximum because of the high press forces involved. The process is used for variety of precision mechanical parts, but bearings and other parts with surfaces that are metal to metal. Sliding contact are good applications because the porosity inherent in these parts provides space for a reservoir of lubricating oil. So this is the video.
Metal powders used for parts production can be a combination of various elemental particles.
So powder metal is actually like we choose the powder metal which is as you consider like what do you want of the metal gonna be.
Pre-alloyed powder, the proper proportion of ingredients is already present in each particle. In either case, additives such as binders and lubricants are usually added. The powder is then consolidated in molds or dies.
Okay, we're gonna talk about this later. Metal powder manufacture, or PM. PM refers to the manufacturing process by which powder metal or metal blends are formed to desired specification through a unique combination of heat and compression to create parts and components that offer improved strength over traditional forged alternatives. So we are on this part. Now we're gonna talk about mixing. So this is like the simple one, powder, choosing one, and then go into mixing. After mix, it's gonna be put into the mold and it's gonna be compact. After that, after the compact, it's gonna be happen into the sintering. Sintering is like you burn it. After the burn, if you remember, if something like metal is burned, it's gonna be like the microstructure is gonna be like expand. After the expand, because of like one atom and one atom, the expand is gonna be like the same one into the same atom or like the same microstructure. So like if you can see here, the microstructure, it has like space between one to another. After the sintering, it's gonna be like this. So that's the introduction of the metal powder manufacture process or powder metallurgy process. Now we're gonna talk about powder blending or mixing. Like we talked before, the ideal powder for parts making may contain a mixture of powders of different metal or alloys, non-metals, different particle sizes, lubricants, and binders. Binders improve the green strength if we remember that the green strength of the unsintered part. Both binders and lubricants are burned of the volatilized, or you can see volatilized is like, you know, when you making casting. If you remember casting, like if you pour, it's gonna be like bubble from that. Because of the bubble, it's gonna be cause like volatile. After the volatile, you need to burn it to make it like clean surface. Blending of these ingredients may be placed either wet or dry. The mixing cycle should be short to prevent the damage to or work hardening of the border particles. Drum double cone, cubical shaped, V-shaped, and conical mixer with rotating screws are commonly used. This is the just like for the mixing. Compacting, you remember? Compact to make it like solid, or you can see it. Metal powders normally at room temperature are introduced and fill a die cavity of precise shape with side walls that are usually straight. A punch of the same cross-sectional shape as the die, and with a close fit to the die cavity, descends into the die and presses the metal particles together. A lower punch which rises to aid in the compaction and later ejection of the part is common. Parts with stepped shapes or French may have more than one lower and upper punch. So this is the fixed die system. The powder gonna be poured into the cavity. Like after that, the powder fill, compaction is happen. After the compaction happen, it's gonna be like injection. The difference between the withdrawal die pressing and fixed die system, it's just different on the die, because the die here gonna be like only stay, like you cannot move it, and this is one like movable. Compacting video, I have this one. It's gonna be filled. After that, pour into the cavity and gonna be push or compact. So that's all. Now we're gonna talk about sintering. The green compact is heated to an elevated temperature in controlled atmosphere. Either a batch type or continuous conveyor furnace may be used. The furnace temperature is well below the melting point of the alloy, involved but high enough and maintained for a long enough period so the diffusion bonding of the metal particles takes place. The metal particles bond securely together and there may be some like increase in density, but of course it's not 100% of dense. The step just burn off, remember? High temp stage and cooling. So it's like burn, holding on high temperature and then cooling. So this is the point of sintering, making the powder particles from spacing or pores or volatile into the solid one. So this is just the process. Repressing. The sintering process results in parts with some shrinkage from the green state as binders and lubricants are removed from the parts. There is also some inevitable distortion from the thermal expansion and contraction that takes place during the sintering. To improve the dimension accuracy of the parts, to improve surface finish, to sharpen certain details, and sometimes to reduce the porosity of the parts, they may be subjected to an additional pressing or calibrating operation. And then can be continued to secondary operation or L1F. It's just secondary operation like cutting, blanking, flange, or like coining. It's like machining. Heat treating with cyanides, like you just try to make it like stronger or cyanide and other things. L1G, powder metal forging. In this process, the sintered powder metallurgy becomes a blend. For forging, the operation involves more drastic deformation than conventional repressing, and at the end, part is heated to forging temperature beforehand. So it's like you have like 75% pre-form from the powder metal. It's gonna be like 75% density. After that, you put it into the die cavity and push by the upper and bottom punch to make it like 99% of density. So it's gonna be like super strong. Powder metal forging, remember, the cavity inside gonna be pushed by upper and bottom punch. So it's just testing first one, and then they're gonna put like the mold or the die. So the work is gonna be so hot, so it can be pressed. So that's all. Electroforming is a process that utilizes electroplating like Sion XC, or I have the more better one technique to make a form shape component, whereas in electroplating and the deposit material is very thin and is left on the surface of the plated workpiece. In electroforming, the deposit of material is much thicker and is separated from the substrate after plating to produce a separate part. So the electroforming is like, this is the positive one, this is the neutral. After the electroforming is activated, the nickel metal gonna be like, the microstructure gonna be stuck into the negative electrodes, so it's gonna be covered the workpiece. Metal injection or MIN, this is the last part, is a metal marking process in which finely powder metal is mixed with binder material to create a feedstock that is then shaped and solidified using injection molding. The molding process allows high volume, complex parts to be shaped in a single step. After molding, the part undergoes conditioning operation to remove the binder or the binding and densify the powders. Finished products are small components used in many industries and applications. So like the metal powder, like the previous one, metal powder, binder, mixed into the granulation. After that, gonna be pushed into the feedstock, get into the injection molding. The injection molding gonna fill the cavity or the mold, and the raw product is produced. It can be cleaning or thermal debinding. After the green body happen into the sintering to make the volatile or the space is gone. So the final product or the clean product is we can use. So this is the video of FIM. This is the injection. I'm gonna fill the cavity. This is after the mix. Yeah, it's gonna be injected into the cavity. After that happen to cooling, and that's all. So that's all. Okay, don't care for everything. So see you next time.